Alright guys, in this video we're going to be using an ICE table to solve for concentrations. So in this particular question, we don't know what those final concentrations are going to be at equilibrium. So it's not as simple as just setting up your Kp expression and then plugging in your Kp and missing ones to solve for a missing concentration. We need to solve for all the concentrations. If we know the starting material and how much we start with, we can figure out how much equilibrium or concentrations we will have. And when you need, what you'll need to do is use an ICE table to solve for that. So first, well, let's read the question. We got at 298 Kelvin, the equilibrium constant for the dissociation of nitrogen dioxide is Kc is equal to 4.6 times 10 to the negative 3. The following reaction was observed, and we have some NO2 gas being decomposed into NO and oxygen. We have a 1 liter container and it's initially filled with 0.5 moles of NO2. And we want to know the concentrations of NO2, NO, and O2. And we should say at equilibrium, probably should the question should say. So at equilibrium, what are going to be those concentrations? We don't know. So first off, I am going to start with my Kc expression. That's going to help us. Okay, so we should have products on top, which will be NO squared. Okay, it's squared because there's a 2 in the front of the NO, and then we'll have O2, and then we'll have NO2 on the bottom, and that'll be squared as well. Okay, that's just going to help us. Next thing we need to do is set up our ICE table or RICE. I'm used to ICE, but you can also see a lot of ICE tables out there. RICE is just for the reactants, the reaction. I like to put it up there just for a little bit of organization purposes. 2NO plus O2. So there's my reaction. I have my different sections here. So initial, or I, stands for initial, so that's what I'm starting with. And in my reaction, I'm starting with 0.5 moles of N2. And I can do 0.5 moles right here, because that's what I'm starting with, my NO2. And that's all I'm starting with. That's my only reactant, so I don't have anything else. So that's going to be a 0 and 0 here for my products. The change, I am going to be losing minus 2x. Okay, I'm putting x because I don't know how much I'm losing, and I'm putting a 2 because for every 2 moles worth of stuff that I'm losing, I'm gonna be gaining as a product. I'll be losing as a reactant, so I'm going to put minus 2x there. Same as my NO, I'm going to put plus 2x because I'm gaining 2 moles every single time. Up here's my 2. And here I'm just going to put plus x because I'm only going to be getting 1 mole's worth every single time. Okay, so my equilibrium will be 0.5 minus 2x. This will be plus 2x, and this will be plus x. Okay, this is how the ICE table is formatted, just for you to help you sort out your variables. Okay, next thing I'm going to do is I'm going to put these variables into my Kc expression. So that's going to be products on top, which will be 2x, and that is going to be squared times x. Okay, I'm getting that from my NO and O2 in my Kc expression. And then I'm going to put 0.5 minus 2x on the bottom. Now, here's the kicker. If you're going to be solving for this, we're going to do quadratic. And we don't have to do quadratic on the AP test, which is really nice. So what we get to do is make an assumption. We're going to assume that this x, that I just erased, is negligible. And the reason we can assume that's negligible is we're going to assume that because the Kc is so small, we can assume that's going to be mostly product, and that this 0.5 concentration is much higher than that will be lost, because it's mostly going to be reactants at the end of this. So let's keep it as 0.5, and we're going to get rid of that minus 2x. Somewhere in your notes, when you're doing this as a short answer question, you could probably just put in arrows negligible loss. Negligible loss. So we can leave it like that. Okay, we know our Kc. I can plug that in. It is 4.6 times 10 to the negative 3. I get that from up here, 4.6 times 10 to the negative 3. And that's going to be equal to 2x squared times x. Okay, algebraically, okay, you got to distribute that in, so it becomes 4x squared times x, so it becomes 4x to the third when you're solving for it. and it'll be 0.5 on top. Okay, now we just need to solve for x. First step you're going to have to do is you're going to have to multiply both sides by 0.5. That gives you, let's see, 0.5 times 4x. Oh, I missed something. Sorry, it is squared right here. So this gets squared. So that one will multiply by 0.5x squared. You're going to get that 1.15, let's cancel, times 10 to the negative 3 is equal to 4x to the third. Okay, going back to my mistake that I just put in. So right here, it is NO2 squared. So I have to make sure my NO2 squared is there. So I'm just putting back in the algebra that I should have had initially. Okay, so that becomes 1.15 times 10 to the negative 3 is equal to 4x to the third. I divide both sides by 4. That gives me x to the third is equal to, it's approximately 2.9 times 10 to the negative 4. Okay, last step, cube root that. I know there's a lot going on here, but we're just solving for x, and x is going to equal approximately 0.0675 molarity. Okay, and that's x. Now, a lot of us will get to this point, and we've done so much math and calculations just to get to this point, and we'll think that's the answer, but it's not, because we got to think back, what are we even looking for in this question? We're looking for the concentrations of NO2, NO, and O2, and that is a lot, and I know this question is very taxing, so stick with me. The concentration of NO2 is going to be found by taking that 0.5 minus 2x. Okay, I'm getting this straight from here. Here's my equilibrium expressions to solve for x and what I have. So 0.5 minus 2x, I plug that in, it becomes 0.5 minus 2 times 0.065. You're going to end up 0.5 minus 0.135. So the concentration is 0.365 molarity, and that is concentration for NO2. Concentration of NO is going to be a lot easier. We just have to do 2 times x, which is 2 times 0.0675, which we will get approximately 0.135 molar. And for O2, the concentration of O2 is simply just x, which means we found the concentration of, 0.065. Concentration of O2 is just the x, which we had found earlier. All right, so much work, guys. I know it's a lot. If you need more help, just come talk to me. We can work another problem step by step. But basically, going back to the beginning, we made a Kc expression. We plugged in the initials, our changes, and our equilibrium. We plugged it back into our Kc expression, and we solved for x. And then we went back to our equilibrium section of expression and plugged that x values in to find the concentrations. So what did we solve thinking back on this? What are these concentrations? Those are the concentrations at equilibrium. So as soon as the reaction finished and they reached equilibrium, these will be the final concentrations of each of those molecules. And that's what we solved. So that's solving concentrations if we have to use an ICE table.